This work is focused on approximate sequential optimization for informative path planning. And we have completely open sourced all code that was used in this work, and it's available at the following repository link. So this work is focused on solving both the adaptive and non-adaptive versions of the informative path planning problem over long horizon trajectories and extremely large graph sizes. To do this, we model the environment as a graph, where we have n nodes in the environment and we have edges connecting the nodes to each other. And so what we've shown here is a grid-based graph, but in the general sense, the graph can be any graph structure. And so in practice here, what the vertices or the nodes of the graph actually correspond to are physical locations in the environment that we're interested in exploring. So for a rover exploring the surface of another planet, these are actual locations that the rover could move to and take measurements. An example a little bit closer to the Earth is in a disaster response scenario. If we're sending an autonomous robot to map the extent of this oil spill, then those could represent locations of movement at a different resolution in this case. So given this graph, we have some start node that the agent is starting at and some goal node. The problem here for informative path planning then boils down to how do we plan this sequence of actions where the actions are what nodes in the graph do we want to visit and what measurements do we want to collect at those nodes. So the ultimate goal here is to receive a path, which is the sequence of nodes that we're representing here as I1 up to IL. And we can have various constraints on the path. So one example of a constraint that we could have is a budget constraint, where we're saying that the total edge cost along our path from node I to node J, we want that total cost along all of those edges in our path to be less than some budget that we're specifying. That's one example of a constraint. We'll talk about some other examples as well that we could have. One other variation that we can have here is that in some cases we might not be interested in making predictions at every single node in the environment, but only at a subset of nodes. So here the orange nodes are representing this vector x in Rm, which are the actual nodes that we're interested in making predictions at. So this is the subset of the environment. Why would this be useful? Well, in certain cases, when either you're planning at extremely fine resolutions or over very large graphs, then one, it's typically not computationally tractable to store all of this in memory and make these predictions, and two, it often doesn't get you that much in terms of a better prediction rather than just subsampling this graph and predicting at a subset of those nodes. So that's why we include this generalization in the problem formulation. So given this setup, how do we actually take measurements now? So what we're saying here is that we have the following measurement model, where at node I in the graph, we receive measurement yi. And so this measurement is characterized by this A vector, this AI, which is telling us how are we going to measure those x values at a given node. So if I'm at node I, how am I going to measure x given my current sensor that I'm using? And we're assuming we have some zero mean Gaussian noise here as well. So with this path setup and with these measurements that we've observed, we can then construct this posterior estimate about what we believe the values of x to be. And if you're familiar with Gaussian processes, this is exactly the Gaussian process mean and covariance. So when we talk about the non-adaptive version of the problem, that's typically planning with some information objective based solely on the covariance matrix. And you'll notice here that this covariance matrix does not depend on the actual measurement values received. That's why this is considered the non-adaptive problem. The adaptive version considers typically both some function of the mean and covariance here to create that objective function. And so we'll talk about both variants of these problems. But just to get a sense here, some of the information objectives come from the optimal design of experiments field, where this is looking at the non-adaptive version here. So regardless of whatever objective we're using, for now we can represent this information objective as 5p, and then we can state the informative path planning problem as follows, where we want to minimize this 5p objective subject to our path being a valid path. That's the informative path planning problem. So before we get into our specific contributions, I think it's helpful to sort of frame the problem in how previous approaches have looked at it. So I've selected and categorized these into some of the main approaches here and highlighted a few of the key papers. All of this work really stems back to the sensor selection problem, where in this problem we're looking at how do we place sensors in an environment to estimate some quantity of interest. So here we're not considering how are we actually moving from one node in the environment to the other. We're just saying that we can place sensors wherever we want in the environment. To sort of remedy this and to now include the path constraints of how are you actually moving from one node to the other, mixed integer programs became a popular solution because you can sort of enforce this integer constraint representing the edges in your graph. Another popular approach is through various approximation methods, where typically these approaches are using some form of a Gaussian process to quantify both the spatial correlation in the environment as well as the information objective, and then using either branch and bound or other heuristics to produce a solution. And then lastly, these learning-based methods have become popular, where typically this involves learning a neural network representation of informative actions offline and then querying that neural network online either in a tree search or greedy-based fashion. And so in the context of this related work, how our contributions and how the work we're discussing here differs is that we're considering additional path and sensor type constraints where we have multiple sensors available to the agent. We're formulating the information objective using Gaussian processes, and we're also considering both the adaptive and non-adaptive versions of the problem. And then we extend our method also to look at the multimodal sensing and multi-agent problem variants, and we're doing this over much larger graphs with tens of thousands of nodes and edges compared to what's previously been looked at here. And so for our specific contribution here, we're first going to discuss this mixed integer program formulation that we develop. And then we show that using this formulation, we can present this convex relaxation of the problem. And we'll talk about why this is useful. So we have this graph-based setup that we're working with. And what we can do here is we can introduce this integer matrix Z here. So Z is an n by n matrix, and all Z represents here is the edges of our graph. So if we index into this Z matrix, then the ijth component of Z represents the edge from node I to node J in the graph. And we're enforcing that Z has to be either 0 or 1. So if Z is 0, that means that that edge is not in our path. And if Z is 1, then that edge is in our path. And so we can include various different constraints now on this Z matrix that define a valid path. And so this limits the length of the path. It enforces that the start and end nodes must be on the path, that the path actually starts and ends at those start and goal nodes. And then we also can include these subtor elimination constraints in there as well. And so these constraints on Z, they're largely coming from the variants of the traveling salesman problem or the orienteering problem. And the novelty here is not in introducing these path constraints, but it's in recognizing that we can use this binary variable Z in our expression to rewrite the Gaussian process covariance matrix. And so that's really where the novelty lies, is in recognizing now that we can use this integer variable Z to pick out the corresponding entries in this Gaussian process covariance expression that relate to the actual areas where we're receiving measurements. And so we can now rewrite the informative path planning problem here as a mixed integer program. It might not be entirely obvious looking at this, but this problem would be entirely convex in the A, B, and D optimal objectives that we showed earlier if it were not for those integer constraints on Z. So what we can do here is we can simply just say, well, instead of enforcing that Z is either 0 or 1, let's just relax this constraint and say that Z can lie between this interval between 0 and 1. And now this problem is entirely convex. So it turns out that this works quite well for the sensor selection problem, and you get a very good solution through this convex relaxation with a rounding procedure. This does not work well, though, when you apply it to the informative path planning problem. So the solution that you get from solving this problem is not really meaningful because it doesn't represent an actual valid path here. The reason that this is useful is because solving this convex relaxation gives us an absolute global lower bound solution to the informative path planning problem. This means that we know for a fact that the true optimal value can be no lower than this lower bound that we've solved for in this convex relaxation. And the reason that this is useful is because this tells us the best that we could ever possibly hope to achieve. And so we make use of this when we introduce this approximate method, because this bound now tells us how good is our approximation actually doing relative to the best possible that we could ever hope to achieve? So how our approximation works here is we start at the starting node, and we're assuming that's all that we have in our path at the moment. We're then going to look at the next node, so the neighboring node, and we say, okay, if this node was stored in our path, what would the objective value be? We compute that objective and we store it in the node. Then we look at the next node and we say, okay, if I just had the start node and this node, what would the objective be? I compute it and I store it in the path. I repeat this for the next node and the next node, and then all of the nodes in the graph. And so notice what this is saying. This is essentially saying, okay, given that I'm at the start node, I could essentially teleport to anywhere in the environment, right? Which initially seems like it's not a very reasonable approximation. But what we do here is that this gives us an approximate reward at each of these values in the graph. And so now we can solve an orienteering problem using these approximate rewards. And we can do this relatively efficiently using dynamic programming. So we solve this orienteering problem and we get some solution. Now the solution here, just solving this the first time, is not going to be very good because this approximate rewards are not very accurate. But what we can do is we can either take the first node or the first 10 nodes here of this solution produced. So let's say we take the first 10 nodes. We store that in our path, and now we repeat this procedure. We now say, okay, given that this is our current path, let's recompute this now. So let's look at the next node right over to me. If I added this node into my path, what would the objective value be? Compute it and store it and update that approximate reward for all the nodes in the graph. Then resolve the orienteering problem, store a fraction of that path in the true path, and then repeat the process. And so that's where this approximation actually gets better as we continue to update this path in this sequential manner. And so that's where we get this approximate sequential optimization method. And so we can look at now, how does this actually perform compared to other methods, and how does it scale to some of the larger graph sizes? So we're showing various methods here on this graph. So just to break this down, let's look at first only this blue method here. So what this blue method is showing, this is solving the exact mixed integer program. So keep in mind, if we had infinite amount of time and ran the exact mixed integer program, we would eventually reach the global optimal solution. Unfortunately, we don't have infinite time, so we limited all of the methods shown here to a 2-minute solution time constraint, and the best objective found after that 2 minutes was reported. So that's what we're showing here, is the solution objective to the exact mixed integer program after running for 2 minutes. What we see is that the exact mixed integer program often takes the full 2-minute time limit here. Our method, on the other hand, is this approximate sequential path optimization method shown in orange. And what we see is that on smaller graph sizes, we're performing competitively with the solution to the exact mixed integer program. And on large graph sizes, we're actually significantly outperforming that solution. Not only this, but we're doing this roughly 10 to 100 times faster than the exact mixed integer program solution. We also compared our method to a few other benchmarks as well, one that uses a Monte Carlo tree search based approach and another that uses a greedy objective. And we see that those perform well on small graph sizes, but they don't scale well to these larger graph sizes. We can also use that convex relaxation lower bound from before. So solving our approximate method gives us an upper bound, solving the convex relaxation gives us a lower bound, and we can now look at the optimality gap here. So on the A optimal objective, we see that for budgets greater than 10, we're within roughly 5% of the lower bound. And keep in mind that this means we're most likely actually even closer to the true optimal solution, because it's not likely that the true optimal lies exactly at the lower bound. So in practice, we're even closer than within 5% to the true optimal solution, in this case where we're solving this on a graph with 1,600 nodes. And then we see that for the D optimal objective, we see a similar thing here where for budgets greater than 10, we're still within 5% of that lower bound objective. We can also look at some of the qualitative results here. This is on the multimodal variant of the problem, where the nodes shown in yellow here are representing more expensive sensor placements. So those are more precise sensors, and as a result, we incur more cost for for placing those. We're also showing the prediction locations in white there. And then we also compared our approach against some recent learning-based approaches. And one that has shown to perform very well is the context-aware attention-based network for informative path planning, or CATNIP. And so CATNIP is a neural approach to the adaptive informative path planning problem and relies on self-attention to capture dependencies in data at multiple spatial scales. Specifically, it does this by forming a context of its belief over the entire domain, which it then uses to sequence local movement decisions that optimize this trade-off between short and longer-term search objectives. And so for even comparison between our two methods, we use the exact setup described in the original CATNIP paper. Specifically, we're using a Matern 3.2 kernel with length scale of 0.45. And the ground truth environment is constructed based on their method, which involves averaging 8 to 12 random two-dimensional Gaussian distributions in the unit square to then construct the true interest map in the environment. And so looking at this here, the objective is to reduce variance in high interest areas. And these high interest areas are defined as regions that have true quantities greater than or equal to 0.4. And so to effectively solve this variant of the adaptive informative path planning problem, the solution methods here have to balance the trade-off between collecting additional measurements in high interest areas that they previously discovered with the alternative of exploring new areas of the environment that they have not yet visited. And so we looked at comparing our method against two different variants of the CATNIP method that they propose. One is the greedy method shown there by CG, and the other is the trajectory sampling variant of CATNIP. We see that across all of the different budgets considered here, our approximate method consistently achieves the lowest variance in these high interest areas, showing that it's more effectively balancing this exploration-exploitation trade-off. We do see that the CATNIP greedy variant has the lowest planning time across all of the methods considered, but also it consistently performs quite a bit worse than the trajectory sampling and our approximate method. In addition, we see that our approximate method is quite close to the greedy variant in terms of planning time, while the trajectory sampling variant requires significantly more planning time. And so we also extended our method to handle adaptive objectives that we've just looked at, as well as multimodal sensing and multi-agent scenarios. So this is one example of a multi-agent setup, which is a relatively simple setup here, but we're showing that we can handle here obstacles in the environment. And so how this is working is that we have these three agents, and they're assuming full communication here between the three agents. And to give you a sense of planning time, to plan a single action for each agent here is taking fractions of a second. To plan the total path, so all of the actions for all of the agents together here took about 5 seconds here to plan. So we can do this fairly efficiently in this multi-agent setup using our approximate method. So the key takeaways here from this work are that these approximations improve scalability while still allowing for these bounds on optimality. And this sequential optimization allows us to also incorporate adaptive objectives and other variants of the informative path planning problem. So we demonstrated the efficiency of our method in larger graphs, showing that we can produce these solutions on graphs with more than 4,000 nodes and 15,000 edges within a few seconds. And so future work here really will include incorporating additional sources of uncertainty, such as localization and energy use uncertainty, as well as more complicated multi-agent scenarios where we either have limited communication between the agents or adversarial agents as well. And addressing these challenges will likely require the development of new approximate methods that can maintain scalability while still handling the increased combinatorial complexity introduced by these factors.